Chapter 8 Chemical Equilibrium 8.1 Dynamic Equilibrium Part 2. At the end of the lesson, students should be able to interpret the curve of concentration, reactants and products against time for a reversible reaction. In Part 1, we have learned that a chemical reaction is said to have taken place when the concentration of reactants decreases and the concentration of the products increases with time. The chemical reactions in which the entire amounts of reactants are converted into products are termed irreversible reactions. In contrast, a reversible reaction is a chemical reaction that can proceed in both the forward and reverse direction. During the course of any reversible reaction, a stage is reached when the concentrations of reactants and products become constant. This state is called a state of equilibrium. This, however, does not mean that the reaction has stopped at equilibrium. In fact, at this stage, the reaction proceeds in such a way that the rate of formation of products from reactants is equal to the rate of formation of reactants from products. This is called dynamic equilibrium. For instance, the dissociation of dinitrogen tetroxide to nitrogen dioxide. Initially, dinitrogen tetroxide is being placed in the reaction bottle. As the reaction proceeds, the concentrations of the nitrogen dioxide increases. This can be seen in the diagram B, where the intensity of the brown color in the reaction mixture increases. After some time, the nitrogen dioxide will also combine to form dinitrogen tetroxide until an equilibrium is reached, where the concentration of nitrogen dioxide and dinitrogen tetroxide remain constant. This is shown in diagram C and D, where the intensity of the brown color remains the same. At equilibrium, the rate of the reactant convert to product is equals to the rate of the product combines to form the reactant. So, the rate of forward reaction is equal to the rate of the reverse reaction. How an equilibrium is established can also be explained using concentration versus time graph. There are three possible situations at the equilibrium stage. First, dynamic equilibrium, when the concentration of product and reactant are equal. Second, dynamic equilibrium, when the concentration of unchanged reactant is larger compared to the concentration of product. The third graph shows dynamic equilibrium when the concentration of product is much higher than the reactant. Taking the dissociation of dinitrogen tetroxide to nitrogen dioxide as an example. At initial, there is only dinitrogen tetroxide. As the reaction proceeds, concentrations of nitrogen dioxide increases. some of nitrogen dioxide can then combine to form dinitrogen tetroxide until an equilibrium is reached. At equilibrium, concentrations of nitrogen dioxide and dinitrogen tetroxide remain constant. The concentrations remain constant because the rate of forward reaction where dinitrogen tetroxide convert to nitrogen dioxide is equal to the rate of reverse reactions where nitrogen dioxide combine to form dinitrogen tetroxide. Note that at equilibrium, the concentrations of dinitrogen tetroxide and nitrogen dioxide remains constant, but the concentrations are not the same.